Welcome everyone. Today, we'll explore the main types of hardness tests used in engineering and manufacturing. These tests help us measure material strength and durability. We'll cover Brinell, Rockwell, Vickers, Knoop, Mohs, and Leeb methods. Let's start with an introduction. Why is hardness testing important? It's a fundamental process in materials science that helps us understand how materials resist deformation and wear. Hardness testing is a fundamental process in materials science and engineering that determines a material's resistance to deformation, scratching, or indentation. It provides critical insights into the material's strength, wear resistance, and suitability for specific applications. Hardness tests are widely used in manufacturing, quality control, and research to ensure that materials meet required specifications. Understanding hardness is essential because it correlates with other mechanical properties such as tensile strength and durability. Industries like automotive, aerospace, and construction rely heavily on hardness testing to guarantee product reliability and safety. This introduction sets the stage for exploring various hardness testing methods, their principles, and applications in engineering contexts. Hardness tests are classified into three main categories: indentation hardness, scratch hardness, and rebound hardness. Each category serves a different purpose. Hardness tests can be broadly classified into three categories: indentation hardness, scratch hardness, and rebound hardness. Indentation hardness tests, such as Brinell, Rockwell, Vickers, and Knoop, measure resistance to penetration under a static load. Scratch hardness, exemplified by the Mohs scale, evaluates a material's ability to resist scratching by another substance. Rebound hardness tests, like the Leeb test, assess the elasticity of a material by measuring the rebound velocity of an impacting body. Each category serves different purposes and is chosen based on material type, sample size, and required accuracy. Understanding these classifications helps engineers select the most appropriate test for their application. Next, let's talk about principle and applications of Brinell hardness test. The Brinell hardness test uses a hardened steel or tungsten carbide ball pressed into the material under a known load. The diameter of the indentation is measured and converted into the Brinell hardness number, BHN. This test is ideal for materials with coarse or uneven grain structures, such as castings and forgings. It provides an average hardness over a relatively large area, making it suitable for heterogeneous materials. However, it leaves a large indentation, which may not be acceptable for finished components. Brinell testing is commonly used in heavy industries like automotive and shipbuilding to assess bulk material properties. Then, let's talk about principle and advantages of Rockwell hardness test. The Rockwell hardness test measures the depth of penetration of a steel or carbide indenter under a major and minor load. It offers multiple scales, e.g., HRB for softer metals and HRC for harder metals, making it versatile for different materials. Rockwell testing is quick, easy, and widely used in industrial settings because it provides direct readings without requiring optical measurements. It is suitable for flat, smooth surfaces and is commonly applied in quality control for metal parts, tools, and components. Its simplicity and speed make it one of the most popular hardness tests in manufacturing environments. Next, let's talk about microhardness testing, Vickers and Knoop hardness tests. The Vickers hardness test uses a diamond-shaped pyramid indenter and measures the diagonal length of the indentation under a microscope. It is highly accurate and suitable for thin materials, coatings, and small samples. The Knoop test, a variation of Vickers, employs an elongated diamond indenter, making it ideal for microhardness testing of delicate materials and thin layers. Both tests require optical measurement and are slower than Rockwell, but they provide precise results for research and specialized applications. These methods are widely used in electronics, aerospace, and material development where detailed hardness profiles are essential. Next, let's talk about scratch and rebound testing, that is Mohs and Leeb hardness tests. The Mohs hardness test is a qualitative method that ranks materials on a scale from 1 to 10 based on their ability to resist scratching by reference minerals. It is simple and inexpensive but lacks precision for engineering applications. The Leeb hardness test, on the other hand, is a portable method that measures the rebound velocity of a hammer dropped on the material surface. It is quick, non-destructive, and suitable for large components, making it popular for field inspections. While Mohs is mainly used in geology, Leeb is applied in industrial maintenance and quality assurance for heavy machinery and structural parts. Key differences and selection criteria. Let's see the comparison of hardness tests. Each hardness test has unique advantages and limitations. Brinell is suitable for large, coarse-grained materials but leaves large indentations. Rockwell is fast and widely used for production parts. Vickers and Knoop offer high precision for thin materials but require optical measurement. Mohs is simple but qualitative, while Leeb provides portability for large components. Selection depends on factors such as material type, sample size, required accuracy, and testing environment. Understanding these differences ensures proper test selection for reliable results in engineering and manufacturing. Hardness testing is critical in automotive, aerospace, construction, and electronics. It ensures components meet durability standards and perform reliably under demanding conditions. Hardness testing plays a vital role in various industries. In automotive manufacturing, it ensures that engine components and gears meet wear resistance requirements. Aerospace applications demand precise hardness measurements for turbine blades and structural parts to withstand extreme conditions. In construction, hardness tests verify the quality of steel and concrete reinforcements. Electronics and microfabrication rely on microhardness tests for thin films and coatings. These applications highlight the importance of selecting the right hardness test to guarantee performance, safety, and longevity of products. Challenges in hardness testing. Hardness testing has limitations and considerations. Despite its usefulness, hardness testing has limitations. Indentation tests can damage finished surfaces and may not represent bulk properties for heterogeneous materials. Portable tests like Leeb may be less accurate than laboratory methods. Environmental factors, such as temperature and surface preparation, can affect results. Additionally, hardness does not always correlate directly with other mechanical properties like toughness or fatigue resistance. Engineers must consider these factors when interpreting hardness data and complement it with other tests for a comprehensive material evaluation. Summary and key takeaways. Hardness testing is an essential tool in engineering and manufacturing for assessing material properties. Various methods, including Brinell, Rockwell, Vickers, Knoop, Mohs, and Leeb, offer unique advantages for different applications. Understanding their principles, strengths, and limitations enables engineers to select the most appropriate test for reliable results. While hardness provides valuable insights, it should be considered alongside other mechanical properties for a complete evaluation. By applying the right hardness test, industries can ensure product quality, performance, and safety.